Okay, if we want to solve the equation 5 minus 3 times e to the x equals negative 4, what might you think about doing first? Blake, any ideas? Sure. We basically, like, when you look at this equation, there's only one x in the whole equation, right? So when there's one x, you want to get rid of everything that's happening to x, undo all those operations, and you do it in the reverse PEMDAS order. So you'd start with anything on the same side as x that's being added or subtracted. Well, that's 5. We'd like to move it to the other side. So Blake says subtract 5. I totally agree. We're going to be left with negative 3 e to the x equals negative 9. Taylor, what might you do next? Yeah, we want to get the base raised to the exponent, the e to the x, all by itself. So we're going to divide by negative 3. So we get e to the x equals now a positive 3. And our last step, we want to solve e to the x equals 3. Raise your hand if you can offer some advice as to what we might do to solve for x. Emily?
Rewrite it as a natural log.
Yeah, when you get down to a base raised to an exponent equals a number, and there's nothing else that you can undo from that side, to break into the exponent and get the x all by itself, you're going to use your logarithm because it undoes an exponent. So we would say the natural log, because it's base e, of 3 is equal to x. If you rewrite it incorrectly, so if you don't know the basic definition of a log in terms of an exponential function, and let's say you rewrite it as natural log x equals 3, that's not very helpful, right? Because you can't do a natural log of x. So make sure that you're kind of aware, like when you rewrite it from exponential to logarithmic, or vice versa, it should then be something that you could calculate, either mental math or in a calculator. What is the natural log of 3?
1.09 or 1.99.
1.099. Okay, so that's our value for x. Any questions about the warm-up that I could answer? This is what I would consider one of the more basic equations. We're going to talk today about solving exponential and logarithmic equations. And this is something that you probably practice quite a bit in Algebra 2, some of those more basic equations. In our notes today, we're going to look at some of the equations that require a little bit more work, or some things that might be new to you that you haven't already seen in Algebra 2. So if you would go ahead and get out your notebook, and we'll go ahead and we'll start with section 4. Today is about solving equations, and then tomorrow we put that to use in some application problems, so some real-world scenarios that are modeled by exponential or logarithmic equations. Like I said, have your calculator out so that you can evaluate these answers with us, and that way you know if everything's working in your calculator. And you can call me over, flag me down if you're not getting the correct answer in the calculator. That might be a calculator issue that we need to address. So we're going to talk about exponential and logarithmic equations in section 4. Tips for solving. Exponential equations. This very first tip is what you guys already did in the warm-up. Isolate the base and its exponent, and then rewrite it as a logarithm. This method works great if you have only one base raised to an exponent. If you have more than one base raised to an exponent in the equation, then some different things can happen. Okay, if they have the same base, there are a couple of things you can try. You can use the one-to-one property, so if it's like a to the x equals a to the y, then x must equal y. And we've already solved some equations like that, like on your quiz that you took last Friday. There was that number 5 on the no calculator section where you had to rewrite so that they have the same base, and then you use your one-to-one property. There are some other problems where maybe you have the same base and you have multiple base raised to exponents, but there's like another term that's being added or subtracted, and so you might not be able to use one-to-one, but you could try to factor it. And we're going to look at an example in our notes today where we have to factor something. Now, those maybe not factoring, but definitely one-to-one property you saw last year in Algebra 2. What you probably didn't see last year in Algebra 2, possibly you saw it in Algebra 3, was what do you do if they have different bases? Okay, how do you solve if they have different bases? And if we come across two base raised to an exponent, and there's no way to utilize one-to-one property or factoring, so we can't rewrite it in terms of the other, then we're going to take the natural log of both sides, and then we're going to use our properties of logarithms. Now, when we do this example in our notes, it's going to seem very similar to when we wrote inverses of rational functions in Chapter 1. So the method we use for solving with those properties is very similar to that method of rewriting and finding the inverse of a rational function. Okay, so kind of that same skill will be helpful. Now, on the other side of the spectrum, we have logarithmic equations that need solving. So here are some tips for solving log equations. Tip number 1, probably the easiest. If you have one log in the whole equation, isolate the log. That would be like what we did in the warm-up. Add and subtract from both sides, multiply and divide from both sides. Make sure that the log is all by itself, and then rewrite it in exponential form. So when you rewrite it in exponential form, you'll be able to solve for x. If logs have the same base, then you'll use the one-to-one property. So if it's like a log base 5 of x equals a log base 5 of y, the only way those two logs are equal to each other is if x equals y, because they have the same base. So that's our one-to-one property. But similar to those problems with the exponentials where, like, what if you have two logs with the same base, but you also have some other term? So like something that's added or subtracted with those logs, and you can't get rid of it, then you won't be able to use one-to-one. So you might need to do some condensing first with logs. Remember that you have a property for logarithms. You can condense them, and then when you condense them, you should have only one log, so then you can rewrite it. So you're going back up to 1. Okay, let's look at some examples, and we're going to kind of call back on some things that we know from Algebra 2. Okay. So our first example, I'm going to skip this one. We're going to do log base 9 of x minus log base 9 of x plus 1 equals 1/2. Now, what I see in this problem is that at the moment I have more than one log, 2 log base 9s. And I'd like to be able to solve, so I'm thinking about one of two choices. Could I use my one-to-one property, or do I have to condense first and then follow with rewriting? Well, the issue for one-to-one property on this problem is the 1/2 on the other side. If I add the log base 9 of x plus 1 to both sides, I still have 1/2 plus all of that, and that's not part of one-to-one property, right? Log base a of x equals log base a of y. There's no other term in that. So this means that I'm going to have to condense first. How will my logs condense on the left side? condense into
log base 9 of x over x plus 1.
log base 9 of x over x plus 1 equals 1/2. Okay. So here they're being subtracted. They're going to condense into division using my properties of logarithms. I'm going to keep log base 9. And what's really great about this is now instead of having 2 logs, I have only 1 log. And when you have only 1 log all by itself, you can rewrite it in exponential form. So this is really, in exponential form, 9 to the 1/2, because you always pick up what's across the equal sign for your exponent, and that equals whatever you're taking the log of, so x over x plus 1. 9 to the 1/2 is 3. Cool. 3 equals x over x plus 1. And then there's a couple of different ways or methods that people might use. Tell me something I could do to solve the equation 3 equals x over x plus 1. And I want to see 5 hands in the air before I call on somebody. Mitchell, what could I do?
Multiply the x plus 1 on both sides.
Sure, I could multiply x plus 1 on both sides. Did anybody who had their hand raised, or maybe also just sitting at your desk, think of something else? The other option that I think people could say is, like, write that left side as 3 over 1, and then you could cross multiply. It's really like a ratio equals another ratio, a proportion. But certainly multiplying by x plus 1 in the denominator on both sides, like Mitchell said, works out. So the x plus 1 on the right cancels out, and then we're left with 3x plus 3 equals x. Can we solve that equation? Yeah, no problem. 3 equals negative 2x. X equals negative 3/2. I want you to look at that answer in the context of the problem and tell me what might be an issue for us if x is equal to negative 3/2. Okay?
And it's a log of a negative number.
Let's pick lots of negative numbers. So when I try to plug negative 3/2 in for x, that very first one is log base 9 of negative 3/2. So it's not part of the domain for log base 9 of x. Or even when I plug it into the other one, negative 3/2 plus 1, it's still negative 1/2. Not part of the domain of that log. So does anybody remember in Algebra 2 what we call those solutions where you did everything right, but the solution doesn't work out? Catherine? Extraneous solution. And so since our only solution turns out to be extraneous, it means we actually have no solution, okay, to this equation. Extraneous I always describe as just like a synonym to the word false, meaning like you did everything right. It's not that negative 3/2 is wrong. Negative 3/2 is right, but when we think about it in context of the problem, it doesn't work in the domain, so it's a false solution for us, not an actual solution. Any questions about that example? Okay. What if I give you natural log x plus natural log x plus 2 equals 1? Take a little time. Try to get somewhere with that. And feel free to crowdsource in your groups. What are some things you're thinking about doing? first thoughts?
Like condense the two logs.
Condense the two logs. This time they condense into x squared plus 2x, maybe you'd write it as, because you're condensing into multiplication. They were two logs that were being added, so now they're going to be multiplied. And then that equals 1. What did you do after that, Jacob? Which looks like and then what does all your information from previous algebra classes tell you would be an appropriate method to solving e equals x squared plus 2x? Did any groups talk about that? Hello, tell me what to do.
Quadratic formula.
Quadratic formula. You know, if you have x squared and x, can you solve by reverse PEMDAS? No, I can't divide by x's, I can't square root both sides, like that's not going to work out for me. Everything you know from previous algebra courses says when you have x squared and x, your main two options would be factor or quadratic formula. One side needs to be set equal to 0 first. So we would do 0 equals x squared plus 2x minus e. And then probably our only option would be quadratic formula here. So we're going to plug this into the quadratic formula. That would be x equals the opposite of b plus or minus the square root of b squared minus 4 times 1 times c. All over 2 times a. Yes?
When you want us to convert e into a decimal, do you want us to keep it as e?
Well, that won't, like, as soon as you do the stuff that's the discriminant, you're going to get 4 plus 4e, right? I would convert it into a decimal. And the only thing I'd say is, like, maybe use 3 numbers after the decimal so that when you're taking the square root of that value, you're not rounding so closely. You can also use your calculator parentheses, or you could use the answer key. If you hit second, I think it's negative, it pulls up your previous answer, so it would pull up all the numbers after the decimal. But yeah, I would say this is negative 2 plus or minus the square root of 4 plus 4e all over 2. And so we might go to our calculator and figure out what 4 plus 4e is. Remember that when you're doing your calculator and you're doing 4 plus 4e, it's like e to the first. Okay, so that comes out to be something like 14.873 is underneath the radical. So you have negative 2 plus or minus the square root of 14.873 all over 2. And then you know that you really have 2 answers, right? So I can do second square root, and I come up with 3.856. Negative 2 plus or minus 3.85, ooh, if I round, 857 all over 2. You should be doing this in your calculator so that you know your calculator and how it works. If you choose to do this for the first time on your own on Thursday during a test, well, I wish you luck. Now, you should simplify this so that you have 2 answers. Okay, negative 2 plus 3.857 all over 2. Negative 2 minus 3.857 all over 2. And I get 0.928. And negative 2.929. Are you okay with where I got my answers? should take both of my answers, remember 0.929 and negative 2.929, and I should remember check them in the original problem. 0.928, any issues? No, good. Negative 2.929, issues? Yeah, that second one and that first one are both going to be negative. So we would cross that solution out and mark it as extraneous. That is a false solution for us. So we really only have one solution. So in cases like that, don't be alarmed to use a quadratic formula with the value of b. And at some point, yeah, you're going to evaluate it. I would say the more decimals you choose, the closer you'll be. Always show your work. Okay, but try to go at least 3 decimals. Okay, next one. E to the 2x minus 3e to the x plus 2 equals 0. Now this is one where those e to the 2x and then e to the x are really like different terms, right? It's like having x squared and x. So they're not like terms. I won't be able to combine them. And I'm thinking I have the same base, e, although I have different exponents there. So I have really 2 options if you look back in your tips for solving. I could try one-to-one property, but with one-to-one property, I need them to be all by themselves, and I've got that plus 2. And it's either going to be plus 2 or minus 2, depending on which side I keep it. So one-to-one property is probably out. My other option that we said for exponentials with the same base, one-to-one property or factor. So you can factor this. This is like a trinomial, right? So we're thinking 2 sets of binomials. What would I multiply together in the first terms to get e to the 2x? What do you do when you multiply things that have the same base? What do you do with their exponents? Add them. So if you added exponents and got 2x, what do you think your exponents were? X and x. So it's e to the x times e to the x. Think about e to the x times e to the x. That would be e to the x plus x, which is e to the 2x. Okay, and notice how nicely that's going to give you your middle term e to the x, right? Okay. Do you have factors of positive 2 that add to make negative 3? Negative 2 and negative 1. And you could do a quick 10-second check of your factoring. E to the x times e to the x is e to the 2x. A negative 2 times a negative 1 will give me positive 2. And then my outside terms would be negative e to the x. My inside term would be negative 2 e to the x, which will add to make my middle term negative 3 e to the x. And now if you get it factored, what do you do with your factors to solve? Set them equal to 0. E to the x minus 2 equals 0. E to the x minus 1 equals 0. This becomes a lot easier to solve. Add those constant terms to the other side. E to the x equals 2. E to the x equals 1. I've got a base raised to an exponent all by itself. Rewrite it as a logarithm. Since it's a base e, it will be natural log. Natural log of 2 equals x. Natural log of 1 equals x. And I could plug those into my calculator and get decimal values. Oh, the second one is 0, huh? What is the natural log of 2?
0.693.
Now, the nice thing about this problem is, since it started off as an exponential equation, think back to what we know from our very first section and what is the domain of exponential functions. The domain of all exponential functions is negative infinity to positive infinity. are we ever going to have to check exponential equations for extraneous solutions? No, they're always going to work because we're not restricted in our domain. So it's really the log equations. If it's originally a log equation, those are the equations you need to go back and check for extraneous solutions. Okay, so we don't always check equations for extraneous solutions. Okay. Last one. 3 to the x equals 7 to the x minus 1. What I'm seeing here is a base raised to an exponent equals another base raised to an exponent. I'd probably check this at first. Even though they have different bases, could I rewrite them so that they had the same base? Because if I could, then I could use my one-to-one property. Can you write 3 so it has a base of 7, or 7 so it has a base of 3? Not really. So then your option is that one where I said, if you're solving an exponential equation with different bases, take the natural log of both sides. So we're going to take the natural log of both sides. Natural log of 3 to the x equals the natural log of 7 to the x minus 1. Think about your rules for solving equations. What you do to one side, you have to do to the other. We're okay by taking natural log of both sides. We could really take any log with the same base of both sides, but since our calculator has natural log, that's what we're going to use. Use your properties of logarithms. So if you have something on the left like natural log of 3x, a property of logarithm says you can do what? Take your power of x and multiply it in front. So we're using our property of logarithms to bring x out of the exponent. So now it's going to be multiplied in front of our log. So x times natural log 3 equals x minus 1 times natural log 7. And this is where it starts to feel like, if you go back and look in that very last section of chapter 1, when we had to rewrite rational functions as inverses, we got to this point where we would like multiply by whatever was in the denominator of the rational function, and then we didn't want to have this like separate x minus 1 anymore. So we're going to distribute the natural log of 7 to both terms there. And back in rational functions, we distributed a y for an x. I think it was a y. We distributed a y into both x terms. So we get x times natural log 3 equals natural log, or maybe x times natural log 7 minus natural log 7. Good morning. Friday, Monday. Oh my gosh. You don't even have school on Friday.
You got me so excited.
I know. Terrible. I apologize. And by distributing the natural log of 7, what's beneficial? What can you do now? How would you solve? I think by condensing, we're kind of like undoing what we already have done. Like we were really expanding by the properties. On both sides, you have what? X. In order to solve an equation, you'd really like x to be on the same side. So when you're saying solve, yeah, we want to solve. How are we going to do that? Let's get x's on the same side. Okay, so I have something that looks like x natural log 3 minus x natural log 7 equals negative natural log 7. Okay, and like think about this in terms of what you know. These natural logs are just decimal numbers, right? So we have a number on the right side, whatever natural log, negative natural log 7 is. And then we have some numbered coefficients that are decimals for our x's. At this point, you could do in your calculator natural log 3 minus natural log 7. And you'd get a decimal, and you could have that be your coefficient to x. You could also factor out the x from both terms if you didn't want to round. So by factoring out x from both terms and just writing it as natural log 7 minus natural log 3, or sorry, natural log 3 minus natural log 7, then I'm not rounding my answer. And then I could divide both sides by that whole piece. So I will do that only because I don't want to round yet. Oh, I'm having a hard time writing right now. More challenges. Natural log 3 minus natural log 7. So on this side, I'll have just x. On the other side, I'm doing whatever negative natural log 7 divided by this difference, natural log 3 minus natural log 7 is. Of course, you could do decimals earlier, you just have the issue of rounding. So if you choose to go decimals earlier, make sure you're choosing to write down as at least 3 numbers after the decimal so that you can get an exact answer. So when I type this into my calculator,
Negative 2.294. Never mind.
I get positive 2.29. I get 7 because I'm waiting to round. Okay, till the very end. So that one requires a little bit more work. And notice how that skill now has kind of popped up twice in writing inverses of rational functions and then also solving logarithmic. This idea of we multiply by something, we distribute only to move it to the other side and then factor out a greatest common factor on the other side, which kind of feels like you're undoing it, but you're not. Okay, so you have an assignment that's on the gold sheet, and you want to work on those problems for tomorrow. Please don't delay in getting those problems worked on so that you know if you have questions leading up to Thursday's test. You're going to follow this up. We've got about 15 minutes with a short activity here in class.